for coming, and I apologize for changing the schedule just yesterday because I just discovered that Roman is going to give a introductory talk on MPS, so I think it's better to change. So I'm Masaki Oshikawa from ISSP. So my name is listed on this workshop poster and web page as program committee member, but I did very little. Maybe I just helped inviting a few people, but otherwise I was acting more like a disorganizer or anti-organizer. But as you saw, sometimes this disentangler is useful. Maybe sometimes we need a disorganizer, but I nevertheless thank Kashima-san and Morita-san and other people who really organize this workshop. Okay, so today I wanted to talk about symmetry. So-called symmetry-protected phases from matrix product state viewpoint. But before going into details of matrix product state stuff, first I give you very rough motivation. Probably most of you know about this, but let me give you some quick motivation. So the idea is we want to classify phases, especially we are interested in so-called quantum phases. That is the ground state of quantum many-body system that phases at zero temperature. Of course, there are infinite number of models or materials, so there are infinite variety of ground states. But we want to classify this ground state into several phases because many different models or many different materials show essentially the same behavior. So, and this has been one of the central programs in condensed matter physics, or StatMech. And one representative model, which probably appeared several times during this workshop, is so-called transverse Ising model. So this is a Hamiltonian, and we want to study ground state. Actually, as already discussed, the ground state of this model is exactly solvable in 1D. In higher dimension, you cannot solve exactly, but in principle, you can do simulation or something. So you can study the ground state of this model. And if there is no first term, if you just have a second term, then this is identical to classical Ising model. And I chose the sign minus here, so the ground state would be just given by ferromagnetic states, in which all the spins are pointing up or down, if you just have this one. But once you introduce this transverse field term, this term flips spin from up to down or down to up. So if you look the ground state in SZ basis, sigma Z basis, then this has the effect of introducing fluctuation. So change gamma, then actually there is a critical point, gamma c. It's a quantum critical point or quantum phase transition point. And for example, if you put a gap, then if gamma is 0, you have classical rising, and in order to make excitation, you need to flip some spin. Then you need finite energy. Actually, for example, in 1D, the excitation costs energy of at least 2 or something. For each bond, you get 2, so 2 times dimension. Anyway, you need finite energy to flip some spin in classical limit. So you have a gap. And if you go to large gamma limit, then all the spins are pointing to x. So again, it has a gap. You need to flip the spin in x direction to create excitation. But if you plot the gap, then you find something like this. So the gap closes at the critical point. So it's a quantum critical point. So this smaller gamma phase is characterized by long range order in sigma z, or spontaneous breaking of Z2 symmetry spin flip. So and this way is this way. Of course, in this limit, the spins are pointing to x direction. So in that sense, it's ordered, but there is no spontaneous breaking of symmetry. So in that sense, this is trivial. So we can, in this model, we can clearly distinguish ordered phase from disordered phase in terms of spontaneous symmetry breaking. So this is most characteristic case of quantum phase function between different phases. But these days, we have found some different examples of quantum phases and quantum phase transition, which cannot be understood like this. That is, you don't have any spontaneous breaking of symmetry, but still you can distinguish different phases. So you change some parameter, gamma dash, and maybe you have again like this, and let's say this phase is trivial, and this phase is again gapped, but sometimes this phase has no spontaneous symmetry breaking and no order parameter, or maybe I should say local order parameter. Then you might think this is again trivial phase, there is nothing, but sometimes this is still non-trivial phase. And this kind of phase is these days often called topological phases. And one indication of topological phase is that you must cross some quantum phase transition in order to go to this phase from trivial phase. And so topological phase is very broad concept, and there are some subset of topological phase. One of them is so-called topologically ordered phase, which includes fractional quantum Hall effect and so on. That is, this phase is very defined without any symmetry. Then there is a class of topological phase called SPT. meaning is already in the wording. That is, by SPT I mean some non-trivial phase, which is distinct from trivial phase, but only it's distinct only in the presence of some symmetry. Some appropriate symmetry. Actually, if you just look at this point, then this is common with usual spontaneous symmetry breaking, like this transfer sizing model. That is, you do have quantum phase transition critical point here, but this is because we have spontaneous breaking of Z2 spin flip symmetry here, and there is no symmetry breaking here. So if you apply magnetic field in Z direction, then you break Z2 symmetry. Then you kill this phase transition. So you can go from here to there without crossing any phase transition. In that sense, this conventional phase transition is symmetry protected. I mean, if you break the symmetry, then there is no transition, and there is no concept of phase, at least well-defined concept of phase. So SPT is very similar to this conventional spontaneous symmetry breaking in this respect, but it's different because there is no spontaneous breaking of symmetry in either side of this transition. And there is no local order parameter like magnetization and so on. But still you need symmetry to protect this. And it might sound strange, but I come to the example. So in order to understand this, so this is today's subject. I emphasize that there is no spontaneous symmetry breaking. In that, this is very different from conventional phases. And to understand this better, yeah.
What do you mean by trivial?
Okay, so by trivial, one definition I want to use is you can change the Hamiltonian, change the parameter in the Hamiltonian, like gamma or gamma prime or something. Then you can change the ground state adiabatically, and if you don't cross phase transition, you can change ground state adiabatically. And if you can adiabatically connect your ground state to product state or local state, like a spin up, product of spin up or something, then I would say it's trivial. Because in the product state, there is no entanglement at all. And of course, in generic point here, you do have some entanglement. So if you cut the system into half and measure entanglement entropy, then it's non-zero. But if this phase is trivial in the sense I explained, then this entanglement is, in some sense, removable. You can adiabatically deform the Hamiltonian. Then at the end point, you have product state, ground state, which has no entanglement. So entanglement is removable in trivial phase.
So in this process, you don't have to specify any symmetry or?
Okay, so when I talk about these symmetry-protected phases, I want to impose symmetry to the Hamiltonian, and you can change Hamiltonian within the given symmetry. Yeah. So this topological ordered phase is some phase which you cannot adiabatically connect to your product state, even if you break order symmetry. So this is more robust. And this is more fragile. Yeah.
Are all the topological phases kept?
Oh, okay, so it's probably it's a matter of definition. I would say there are gapless but still topological phases, but it's more difficult to describe or classify. So I think the first problem, at least for, well, for theorists, is to classify gapped phases. And so here I restrict myself to gapped phases, but most of the papers on SPT or topological ordered phase is about classification of gapped phase. But there must be some interesting things in gapless phase, and I want to classify them, but it's harder problem. So. Okay. So I want to understand this, and to understand this, actually, there are examples in one dimension, and one-dimensional system is easier to understand in many respects, analytically, numerically. And in fact, this can be understood in terms of matrix product state, which was introduced by Roman. So in 1D, actually, there is a theorem which I'm not going to prove, but I just give you a statement. The statement is that in 1D, okay, so of course, if you introduce infinitely long-range interaction, then anything can happen. So my discussion is restricted to class of Hamiltonian with some short range or finite range interaction. Then there is a theorem which says that basically there is no topologically ordered phase in 1D. That is any ground state can be if you don't impose anything. That means that there is no topological ordered phase in this sense in one dimension. But still, if you impose some symmetry, then there are phases which don't break any symmetry but still distinct from trivial phase. That is nothing but SPT I just introduced. So I want to understand this. Then, as I discussed for the question a few minutes ago, first we want to classify gapped phases. And, then there is another useful theorem in one dimension that says that basically any gapped for any 1D model with finite range interaction, you have the ground state. Of course, in general, you cannot exactly solve the ground state, but there's a theorem which guarantees that you can approximate this ground state to arbitrary precision using MPS. That means that, of course, in order to get exact result, you need to increase this chi or largely this bond dimension. But we are usually interested in sum-like limit or infinite long system. And of course, if you increase the bond dimension as exponential system size or something, then it's trivial that you can represent any state. But this theorem says that even for infinitely long chain, you just need to increase chi as a function of the precision you want. So chi must be bigger than some function of precision you want. Well, of course, I'm not even giving the statement precisely, but roughly speaking, this the statement. So because of this, when you want to classify one-dimensional gapped phases like this, then you only need to classify matrix product states. What? Yeah.
So you mean that for fixed precision, the chi, the required chi doesn't scale as the system side.
Yeah.
So it's order 1.
Yeah. That's the point. Because if you fix the system size, then of course if you increase chi, then you can get arbitrary precision. That's kind of trivial statement. But, so because of this, what I want to do is so if you want to classify symmetry-protected topological phases in 1D, then this is basically classification. Matrix product states in the presence of some symmetry. That's why matrix product state can be useful. And as I want to emphasize in this lecture, of course MPS, well, in general tensor networks are very useful tool as a basis of numerical calculation. But not only that, actually matrix product state can be also useful even if you don't do any numerics. You can actually classify phases using this MPS language, and hopefully also for tensor network. But so MPS is of course one special case of tensor network, but in 1D we have a lot of understanding. So not only numerical calculations have higher precision, we understand the mathematical structure of MPS better than other variation of tensor network. So we can actually prove many useful theorems. And I want to introduce just a few examples of application. Okay, so already Roman introduced MPS, so I don't have to repeat the introduction, but I'm going to use a slightly different notation. So here I want to use slightly different notation. That is, this MPS is given by product of this gamma, so this matrix of MPS and lambdas. This is a product of matrices, and then so this Mn is physical index. So this corresponds to state Mn at site n. I'm interested in maybe infinite systems, so I don't specify the boundary condition, but you can consider periodic or open or whatever. So in this notation, basically gamma lambda corresponds to matrix A, which Roman introduced. And also a bit confusing, but in this notation, actually, if you compute if you do symmetry decomposition and compute, for example, entanglement spectrum, it's given by lambda squared, not lambda. Oh, and I forgot to say that. So this lambda is, as already introduced, this is a diagonal matrix. With some non-negative entries and gamma can be. So graphically, this means that we have some gamma matrix with some physical index m, and then I multiply with lambda, gamma, and so on. So some people put these two together to call it A. It's just a different convention. Okay. Then, as Roman explained, you can calculate correlation function and so on. Or, in fact, first you need to fix a normalization of a function and so on. And that can be computed using transfer matrix. So, and this transfer matrix, actually you can calculate in two ways. So you can consider transfer matrix from left to right or right to left. And either way you can do calculation. So you can define transfer matrix for the calculation from left to right or right to left. And this transfer matrix, so you can write like matrix, but you can use a slightly different notation. That is so this is a element of, so this can represent transfer matrix, because if you take inner product between blue and cat, then this is a unit, and you repeat this structure, so this gives you the transfer matrix. And as Roman explained, you have dimension chi here. So actually this is mapping from dimension chi, mapping from the space of dimension chi square to another space of dimension chi square. And that can be represented as mapping from matrix to matrix. That is, we can define some mapping of matrix, which is given by so you sandwich some matrix. So Y is chi times chi matrix. Then you sandwich this matrix with lambda, lambda, and gamma, and gamma. And this gives you mapping from this space to this space. Also, you can also define the transfer matrix into the opposite direction. If you expand this in basis, then you can see. So these mappings corresponds to transfer matrix appearing in the calculation of this overlap. These epsilon bar mapping high dynamic matrix. And this is equivalent to considering the transfer matrix. It may be a bit confusing, but when you say transfer matrix, this is a huge matrix mapping chi-square dimensional vector to another chi-square dimensional vector. But the chi-square dimensional vector can be rearranged like a matrix. Then this is just a linear mapping from matrix to matrix. Then, so this is for any MPS. You can define these matrices. Then already several people, I think, discussed so-called canonical condition. That is, so MPS has some gauge degree of freedom, so you can represent the same phase using different matrices. But you can fix this ambiguity by imposing the canonical condition. That is, I require my MPS to satisfy these simple properties. That is, the unit matrix is IN vector of this matrix. So this is a canonical condition. You can start from any MPS and do the gauge transformation. You can satisfy this condition. And furthermore, I want to impose stronger condition to MPS because I want to avoid discussing something like a cat state, Schrödinger cat state. Superposition of up and down, dead cat and alive cat. So, from now on, I want to consider so-called pure matrix product state. And I go to explain what pure MPS means. So for MPS to be pure, it has to first satisfy this lambda matrix is strictly positive. That is, the original condition was that you can always make the diagonal element of lambda non-negative, so it can be zero. But you can always omit zero sector. So you throw out unwanted dimension, then you have only positive entry in this lambda vector. So strictly positive. So in this case, this lambda is diagonal with positive element, so this becomes invertible. And so this is technical. It's almost trivial that you can always do this. But next condition is maybe more non-trivial. That is, so we have this eigenvalue, but so epsilon and epsilon bar has largest by largest in absolute value. Eigenvalue 1. So all the eigenvalues of epsilon and epsilon bar has absolute value smaller than 1, and you have largest eigenvalue 1, and you already have this eigenvector. So this unit matrix is eigenvector of epsilon and epsilon bar with this eigenvalue 1. And by pure MPS, I mean this eigenvalue is eigenvector is unique. There is no degeneracy in eigenvalue. So this is a maybe more meaningful condition. And what this means is probably clear from what Roman explained in the morning. That is, ratio of the eigenvalue is related to the correlation length. So you have largest eigenvalue 1, then second largest eigenvalue gives you the leading decay of correlation function. And so if you have degenerate eigenvalue, if you have two eigenvalues of eigenvalue, two different eigenvector with eigenvalue 1, that means that you have some infinitely long correlation for some operator. So that means that no. So you can rule out Schrödinger cat-like state or superposition of up and down spin, so GSD kind of state. So in that sense, it's not about main naming, I think. So this is a pure state. You just have single state, not superposition of completely different state. So this is a kind of natural condition. So physically, if you have degeneracy of eigenvalue 1, that signals that you have actually superposition of macroscopically different states. So you just pick one of them, then you can satisfy pure condition. Okay, so these are conditions. But as we will see, actually this condition is very strong, and this gives us many. now we have tools to describe some symmetry in 1D. So let's now discuss what if you have certain symmetry. And there are various kinds of symmetry, but as a simplest case, I want to first discuss so-called global symmetry. That is this is like a spin rotation. So when you talk about spin rotation symmetry in some spin system, you rotate all the spins simultaneously by same angle around the same axis. So mathematically it's given by product of unitary operators acting on each side. So this small u is unitary acting on each side. For example, spin rotation or something, and you just consider product. So you rotate all the spins by the same angle, for example. And then suppose you have symmetry, and by definition of SPT, you shouldn't have spontaneous breaking of this symmetry. So your ground state must be invariant under this symmetry. So my ground state is basically invariant. You might get some phase.
Excuse me,
Yeah.
I have a question about wording. What is local symmetry in this context then?
Oh, okay. Maybe, okay, so maybe the wording is not quite the best. What I should say. Yeah, so unitary, so, but okay, so it's, okay, so appropriate word is really the product of local unitary, but I don't know how to say it.
I just didn't know what is the standard wording.
Okay, I'm not sure. So the other case, which is somewhat different, but I can do the similar discussion is, for example, time reversal, which is anti-unitary, or spatial inversion. So spatial inversion is very defined unitary symmetry for entire system, but you cannot write like this, so it's a bit different.
Yeah.
But it's also global, so.
Yeah.
Okay, so yeah, maybe there is anybody knows. Maybe there is better. Sorry, yeah. Thanks for continuing. Maybe recall later. Anyway, here I want to consider this.
Okay.
Then you should have this. The ground state must be invariant under this symmetry. Then what you can say is that is product. So this is like fidelity. So you do this transformation on your ground state, then take inner product with the original ground state. Then this is some phase factor. So for infinite system, actually, this phase may not be well defined, but here I'm a bit sloppy. And, anyway, you may have some phase factor that, but if the ground state is invariant, then the amplitude, this inner product, should not vanish at that point. So that already gives you some interesting consequences, because you can represent this inner product in terms of MPS. So in terms of MPS, you have gamma, lambda, gamma, well, maybe I should say this, gamma dagger. and then you have physical index, but you sandwich with this product of local unitary. So you need to insert this local unitary. So this is what you get. And then you can calculate this overlap, again using transfer matrix. But now the transfer matrix becomes different because this is now a repetition of this guy. Or maybe I include it here. So now this is the unit of repetition. So this gives you new transfer matrix. And again, you can define transfer matrix from left to right or from right to left. But you can define a similar quantity. So for simplicity, let's take the, so this U is unitary. Then you can always diagonalize this. So you can take some appropriate basis in physical state so that this unitary becomes diagonal. Then this transfer matrix can be written like, so I'm using J because I'm moved to a new basis which diagonalizes unitary, but this is like N in different bases. So I put this phase factor, then gamma J in this basis, then lambda, then X, lambda, J down. So if you drop this, then this is exactly like original transfer matrix, but because I inserted this U, now I need this factor. So so this is a new transfer matrix. Then I want to know the eigenvalue of this transfer matrix. So to do that, so suppose this is lambda times. Okay, so suppose function U of, there are some eigenvector and there's some eigenvalue. Eigenvector, but actually matrix. Then you have this equals to this for x equals to 2. That multiply lambda square v dagger from the right. So to both sides I multiply this one. Then take the trace. So this is a matrix, but I can take trace. This is also a matrix. I can take trace. Then I still have some identity. And then you can take absolute value of both sides. Then I'm just taking absolute value. And then this is lambda square with dagger, but it's maybe like lambda times lambda with dagger. Then this trace can be interpreted as a trace of product of two matrices. That is, I take this is one matrix, and so because trace is cyclic, you can put the product of lambda v dagger gamma lambda as one matrix. So this is product of this matrix times this matrix, then take trace, and this is like if you expand matrix into vectors, it's like an inner product between two vectors. So so this is like trace of M1. Not unique, but let's say this part was M1 dagger. This part is M2. Then M1 is lambda v dagger. M2 is then this is like inner product between two vectors. So for inner product of two vectors, there is this useful Cauchy-Schwarz inequality. v1 dot v2 absolute value is less than v1. So this is trivial like inequality geometry, but you can apply this to more higher dimensional vector space and also to this inner product between two vectors. Then this product can be bounded by trace of so length of this vector.
So you still have the sum of j. Sum of
Yeah,
j.
yeah. Right. Yes. Yeah, but this is yeah. So I think I can do this.
You can do it. You can do it because it's a single summation. If you do it, you have double summation.
I think it's like a inner product of two vectors.
Vector M1 and M2 have three indexes.
Yeah,
Then
yeah.
came from
So
matrix and
yeah,
one
I
came
think
from
yeah,
J.
yeah. Okay, yeah, that's right. Yeah. You're right. So this summation over J and trace is like inner product in chi-square times D.
Yeah, so your vector V also has an index J.
Yeah, yeah,
That's
yeah.
what you mean.
Yeah, yeah. So well, so trace is summation over indices of this matrix chi times chi, and then you further take this J summation. So actually this I now regard a vector in chi-square times D dimensional vector. Yeah. Then this trace plus this summation is regarded as inner product in this chi-square times D dimensional space. Yeah, actually, yeah, that's, I think it's clear also from next line. So maybe I shouldn't write this, maybe super trace, including the summation over J. So maybe this notation. In fact, the right-hand side is like a trace of this dagger times this one. So, lambda J. Here, if you take product with Hermitian conjugate of this M1, then you have complex conjugate, so this theta J vanishes. Half times so the right-hand side of Cauchy-Schwarz inequality looks like this. And but you have this summation over J, and if you look this very carefully, then you find something you might remember, that is summation over J of this guy. Okay. And summation of j over this guy. So maybe this is easier. So this is gamma lambda square gamma j dagger, and then summation over j, which is actually nothing but this mapping epsilon, and just unit matrix is inserted. And by canonical condition, we already require that this must be unit matrix. So we can just eliminate this, replace this with unit matrix. And similarly, so this is also epsilon or something, and epsilon of actually v dagger v. So this is nothing but the epsilon of v dagger. But so this is like epsilon of v dagger times lambda squared. Still need a trace of epsilon of times trace of so the right hand side is like this. But then we also require that this epsilon has largest eigenvalue 1, and the other eigenvalues are smaller in absolute value. So that means that this one is bounded by v dagger v, because this v dagger v is a positive semi-definite matrix. So, this can be replaced by trace of v dagger v times lambda squared 1/2 trace of v lambda square v dagger 1/2. But because trace is cyclic, actually these two are the same. So this is nothing but trace of v lambda squared v dagger. And so this was upper bound of right hand side. But the left hand side was this. So from this you can conclude that first lambda must be smaller than 1. Or, yeah. But this is of course physically obvious. So otherwise, if you apply unitary, then amplitude with, so this was like fidelity. So this was this eigenvalue gave transfer matrix of amplitude between psi and u psi. So if this is bigger, then you get the bigger amplitude between psi and u psi than psi and psi. That's of course physically nonsense. So of course this is physically expected. This follows from this argument. But not only that, so this must hold always. But if I require my ground state wave function to be symmetric, that is invariant under this operation u, then amplitude must be the same as psi psi, at least if you forget about phase. So the requirement of u psi is e to I theta psi symmetry. That requires actually lambda to be 1. So you must have eigenvalue lambda equals 1 for my original ground state to be symmetric. If this is the case, then actually amplitude does not vanish with respect to original amplitude of the time. So this is the recurrent. Then, if you require this, we have used several inequalities. We have used inequality twice. That is Cauchy-Schwarz inequality here, and also inequality here. And both inequality must satisfy equality equal to achieve this equality. So, can I write here? Lambda equals 1 requires first epsilon of V must be V. Because the largest eigenvalue of epsilon is 1, and the V must belong to that largest eigenvalue. Otherwise, this becomes strict inequality without equal. Then lambda cannot be 1. So this must be satisfied. And then, by the requirement of purity of original NPS, this V must be proportional to unit matrix. So basically, so from this, there is some degree of freedom in choosing V, but from this, V is essentially unit. And also another condition is that this Cauchy-Schwarz inequality must also have equal sign. Otherwise, you cannot have lambda equals 1. That means that this M1 and M2 are parallel vectors with each other. So on this, basically M1 and M2 must be parallel or proportional. That means that alpha times E2 is theta J lambda. So these two matrices must be proportional to each other for any J. And this alpha is proportionality. Then from this, so you can take inner product with itself in each side. So alpha squared times lambda times V lambda A daga lambda equals to daga. And then again you can take summation over J. Then yeah, this again becomes a familiar form. I choose V to be unitary, then this is just unit matrix. And, this is again unit matrix. So it's just lambda v daga v lambda. This is, so this proportionality constant alpha must be 1. So from this, what can be said is that because absolute value of alpha is equals to 1 means that the alpha can be written like exponential minus I theta, or some angle theta which is independent of j. Then what we have shown is so I'm looking at this equation. So yeah, I'm running out of time, so I'm skip next step. But using similar step, I can also show that this V and lambda should copy. So that's I don't enough time, so let me skip this. But you can derive using similar discussion. Then we have this proportionality relation. So E2 minus I theta times theta j times lambda gamma j lambda vega is same as lambda vega times lambda. And also lambda is invertible, and lambda and v commutes. I'm skipping, but you can show this. Then you can apply lambda inverse and eliminate this. Then what you can obtain is e to I theta j times gamma j is some phase remove here, and then you have this veta and this gamma j v. So you eliminate this veta by multiplying v from right, and I didn't have time to show that v and lambda commute, so yeah, eliminate this lambda. So at the end of the day, you get this simple condition. And this is representation of this is how the symmetry of the state is expressed in terms of MPS. And maybe I took this particular basis in which this unitary is diagonal. So in more general basis, this can be written like some representation of unitary. Small u prime is some representation of my unitary in physical space. And so this unitary transformation of this matrix is equal to some phase, which is determined by my unitary. And this unitary V acting on bond space. So this is a condition you get when you require purity of MPS, and then your MPS to be symmetric under this transformation. And once you get this relation, this is kind of natural. Because what this says is that I have this gamma, and then apply unitary operator to this physical space. And this relation means that you can express the same thing as some phase times this matrix product, but without any unitary acting on the physical space, but acting on V. So you insert some new unitary V. And so to show the reverse is easy. So if you have this relation, then your MPS is invariant under symmetry, because this unitary cancels with the unitary operator next. And for that, this condition is very essential. But once you have this, then it's easy to see that once you have this relation, your state is symmetric. But to show the reverse, that is, if you have symmetry, you must have this condition. It's harder, but using these inequalities, you can somehow prove. And this is very useful relation. So from this, what can be said is that so V must be the representation of the symmetry group acting on the bond states. And it has to satisfy associativity, that is, if you have U1 and U2, then it has to be theta 1 plus theta 2, and V U 1 But this must also can be written theta of 1 plus 2 the v of u1 u2. So if you apply two operations in sequence, then if you apply this relation twice, then you get something like this. And but product of U1 and U2 is also element of the symmetry group. And so if you apply this relation directly to the new element, then you get something like this, and they must be the same. From this, basically, this V corresponding to the product of two elements must be the same as the product of these unitaries. So in that sense, this V must be representation of the symmetry group. But there is one caveat, that is you have product of V and product of V that are here and there. So V of U1 times V of U2 must be basically like V of U1. But there can be some phase. So there can be some non-trivial phase, because even if you have some phase factor, this phase factor cancels between here and there. So you can, in principle, have any phase factor. So if you don't have this phase factor, then it's standard representation. But you are allowed to have some phase factor. Sometimes you can eliminate this phase factor by redefinition, but sometimes you cannot remove this phase factor. Including this possibility, this kind of representation is called projective representation. So you have some phase factor, and
Excuse me?
yeah.
From the derivation, it looks like the phi 1 and phi 1, 2 is just a summation of phi 1 and phi 2, but why do you write in that way?
Because the condition is that this and this must be equal. So even you have some non-trivial phase factor, which is not just sum.
Oh, I see.
That does not contradict with this. Yeah. So in general, this phase factor is allowed, and in fact sometimes appear. That's a point. For example, if you consider, for example, spin matching, then we have a global spin rotation symmetry. But actually, it's well known that okay. So in case of half integer spin, the symmetry group should be called rather SU2, not SO3. But for integer spin chain, representation of spin can be understood as SO3. So you have just global spin rotation SO3 symmetry. But it's well known that SO3 has non-trivial projective representation, which corresponds to actually representation of SU2. In fact, it turns out that okay, so this protects this Horden gap phase. Which contains this spin 1 AKT, which was already introduced by Roman and many other people. So this particular state is one simple example of MPS, and this is element of Horden gap phase. And this is SPT, which is protected by this SO3. In the sense that for this AKT phase, you can apply this analysis. And what you find as this representation V is actually SU2, not SO3. So in that sense, in AKT state, you have non-trivial representation of SO3. So it cannot appear in trivial state. So if you consider trivial state, it's just product state. So each site, each spin 1 transform according to SO3, not SU2. So in trivial phase, you only have SO3 representation. But if you construct this state, then you find non-trivial projective representation of SO3, that is SU2. And physically, it corresponds to H spin. If you cut one bond, then you have free spin 1 half that correspond to this SU2. But it turns out that you don't really need full SO3 symmetry. Full SO3 symmetry to protect this phase. You just need so this subgroup consists of pi rotation around x, y, and z axis. So it's Z2 because if you apply pi rotation twice, then you get back. But you have 3 axes, so it might look like Z2 cross Z2 cross Z2, but it's Z2 cross Z2 because if you apply pi rotation around x axis, then y axis, then you get rotation about z axis. R x pi r y pi is r. So this is rotation about. And in terms of representation of SO3, this, of course, this is the same as Ry pi Rx. So in either way, if you rotate pi around x-axis, then y-axis, then you get pi rotation about z-axis, and it doesn't depend on order of rotation. But it turns out that for equality state, so we have three, so physical space is spin one space, so it's three-dimensional space, and that can be combinatorily written as gamma alpha is just a Pauli matrix. Then can be shown that in this case so this unitary acting on bond space, which corresponds to, let's say, Rx of pi, turns out to be, for example, sigma x, and V operator corresponding to rotation about z-axis can be taken as sigma z. So this is actually natural. So if you consider rotation of spin one half by angle pi, then you get the exponential of sigma x, and you usually have some phase factor, but this phase factor can be absorbed by the definition as far as this subgroup is concerned. So you can take this. But for this, actually, you get non-trivial phase factor. If you take this order, then this is sigma x, sigma z. But if you consider multiplication in opposite order, then this is sigma z, sigma x. So the sign is flipped. So this is not equal, but you need to get minus 1. So this is the example of non-trivial phase appearing in projective representation. And this phase is, of course, cannot be absorbed by redefinition of this guy, because each side has same width, so you cannot eliminate. So this is one example of projective representation. And as long as this V matrix corresponds to non-trivial projective representation of the symmetry group, then basically you cannot adiabatically deform this to trivial state, because trivial state is product state, and there is no place for non-trivial projective representation. So if you want to move from this AKLT spin one AKLT state to trivial state, you have to cross some phase transition somewhere, or you break the symmetry, then you can avoid everything. But as long as you have global Z2 cross Z2 symmetry in this sense, then you need to cross phase transition in order to go to trivial phase. And at the phase transition point, the representation of this V changes from non-trivial projective representation to trivial in the sense of projective representation without this sign. So the point is that at a critical point, you have infinite correlation length, so you can no longer apply the theorem that you can approximate infinite size system by finite dimensional APS. So you might use Mera, but all these discussion assumes that you can use finite dimensional APS. So that assumption breaks down at the critical point. So if you have phase transition, then you can move from these two different representations. So that's one way to look at symmetry protection. So one mechanism is that if you cut a bond, then at the boundary, if non-trivial projective representation appears, and then it's symmetry-protected topological phase. And that precise meaning of that statement can be formulated. And yeah, there are many more interesting stuff, but I think Frank Borman is coming next week, and he is, I think, give you more development along this line. So thanks for attention.
Question? Let me start again. What would be the first obstacle when you would like to extend this kind of argument to higher dimensions?
Well, first is of course you don't have this MPS representation. Well,
right, but somehow you can define something similar in each direction separately.
Right, yeah, I think, yeah, well, so at least for finite width system, you can maybe still represent the two-dimensional system or something using this language, but with this, I think you can only capture some subset of two-dimensional SPT. That's essentially one dimension. I think Soichiro is going to talk about something like that next week. But there are more non-trivial SPT, which is essentially two-dimensional, which requires another different language, I think.
So how much do we know about the transition between the trio phase and SPT?
You mean universality class and so on?
Right.
Yeah, that's a good question. So of course in 1D we know conformal field theory. So for example, in this particular case of Horden gap system, we know what is phase transition universality class when you add some, anisotropy or something as for each case. But I don't think we have a unified understanding of restriction on the possible universality class given the characterization of gapped SPT on both sides. I think that's interesting question. Yeah, we know for many cases, but as a separate problem, and maybe there is something unifying principle. But as far as I know, there is no such formulation yet.
Any other question? Should be many.
Can I ask a second
Yeah,
question?
sure.
So it seems that your lecture today is restricted to bosonic system.
No.
So if I remember right, sometimes if you think of the bosonic system, for instance, spin system, as a system of fermions, then, for instance, in this case, the Horden phase is actually adiabatically connected to a trivial phase, to a band insulator of fermions. I think Adam Roche has a paper about it.
Yeah, I think yeah, but still, if you impose appropriate symmetry, I think you can still protect. But it becomes more fragile. Yeah, I don't remember exact details.
So
yeah.
is it true that, in a sense, whether a phase is trivial or symmetry protected depends on the point of view, whether you regard it as a bosonic system or regard it as a fermion system?
Yeah, I think So I think your question is this spin system actually physically arises from electrons in
right.
at least in condensed matter magnetism. So each electron carries spin, and if you introduce appropriate Hubbard-U type interaction, then you can derive spin model as a low energy effective model of electron system. But of course, Hilbert space of electron system is wider. So it's possible that you cannot go from this phase to that phase within this bosonic or subspace without crossing phase transition. But if you go to electron Hilbert space, you have more possibilities. So sometimes you can cross. But even for that system, I think if you have sufficient symmetry, you can still protect. But it becomes more fragile. Yes.
No, I don't really understand this argument. When you move from a spin representation to formulate more broader, Hilbert space, what kind of symmetry is changed or broken or?
I can probably answer that one actually.
Yeah.
I'm going to comment on the previous question that generically what happens if you've got say charge fluctuations or fermions in the system as well, then your V here ends up as like as a direct sum of a projectively trivial and a projectively non-trivial part. So the charge fluctuations basically destroy the symmetry protection for this particular symmetry. So you don't have the dihedral symmetry, you don't, or the SU2 anymore, but you can still have parity, spatial spatial
So
inversion.
time reversal probably works.
No, the same argument also applies to time reversal as well. If you've got or if you've, because then your entanglement spectrum ends up looking like a mixture of, say, basically half integer and integer spin reps, and the integer spin reps are time reversal symmetric, and the half integer are anti-symmetric. So again, you get it, this sort of direct sum of
the inversion one is
representations. Yeah, but you can be protected by spatial reflection.
That I didn't discuss, but you can extend this analysis to inversion symmetric.
Any other questions? Okay. Thanks, Sam. Thanks, Charles.